Hello everyone. Today we are going to discuss about algebraic and transcendental numbers. And here is where the story begins. And these are our table of contents. I divided into 4 parts. The first part I am going to discuss about a number's tale. A number's journey. Once upon a time, in the magical world of numbers, there was a young number named the square root of 2. And he is very cute, and this is the picture of him. And he lived on the continent of algebra with his friends, integers like 3, fractions like 1 over 2, and even imaginary numbers like I. And this picture is about the continent of algebra. Every number on this continent has a special connection. They could trace their roots back to a polynomial equation, like this. Anx to the power of n plus to the a0, and the coefficients are all rational numbers. But one day, the square root of 2 heard about numbers living far away on the transcendental islands in the ocean of infinity, and these numbers had no ties to polynomials. Curious, the square root of 2 set out to learn what made these numbers so different. As the square of root 2 prepared for his journey, he thought about his own roots. I am an algebraic number, he said. I solved the equation x squared minus 2 equals 0. He looked around at his friends. The integer 3, who solves x minus 3 equals 0. The fraction 1 over 2, who solves 2x minus 1 equals 0. Even the imaginary number I, who solves x squared plus 1 equals 0. We are all connected to our roots, the square of root 2 realized. As the square root of 2 reaches the ocean of infinity, he saw the transcendental islands. Look at the picture. These numbers were unlike anything he'd ever seen. No polynomial equations could connect them back to algebra. They were free, floating in the infinite vastness of mathematics. And look at the examples. Take pi, said the wise number. It's the perfect example of a transcendental number. It appears everywhere. Circles, waves, even quantum physics. But it has no algebraic roots. And don't forget E, added another number. It governs growth, interest, and nature, but it is not an algebraic number. As the square root of 2 sailed closer, he realized the ocean was vast. I thought transcendental numbers were rare, he whispered. Not at all, said a passing transcendental number. We are everywhere. Algebra may seem big, but it's just a tiny island. Most numbers you will encounter are transcendental. Wait, most numbers? Guessed the square root of 2. Yes, the transcendental number said. Algebraic numbers are the exceptions. Actually, we are the rule. And so, the square root of 2 returned home with a new understanding. And the second part is the magic of transcendental numbers. The first transcendental number was discovered by French mathematician Joseph Joubert, and he constructed and proved that a specific number is transcendental in this form. And this number, when written as a decimal, look at this. Using Joubert's method, we can construct a large class of transcendental numbers, and these numbers are called Joubert numbers. Another interesting number is called Hilbert number. Look at his picture. The number may look simple, but it is actually a transcendental number. This was proven using a result called Gilford's theorem, which states that if A is an algebraic number and B is an irrational number, then A to the power of B is transcendental. In the case of it, 2 is an algebraic number, and the square of 2 is irrational. So by the theorem, the 2 to the power of the square root of 2 must be transcendental. And the third part, we are going to talk about transcendental numbers in everyday life. First, let's play a simple game with numbers. Imagine that we take the number 10 and split into equal parts. For example, we split into 2 parts, which is 5 times 5 equals 25. You can also split into 3, 4, or more parts and multiply the results. What happens then? See 2 parts, 3 parts, and we get the different results. Then we observe these results. We find that as we increase the number of parts, the product first grows, reaches the maximum while splitting into the 4 parts, then starts decreasing. Why is this happening? Is there some hidden rule behind this? To find out the mystery, first, we should set up a function. When we split the number 10 into n equal parts, each part is x equals to 10 over n, and the product of all parts is Pn, which is x to the power of n. Now we want to figure out, for which n does this product become the biggest? And we use the logarithms to make the math easier. And we expand it. And we get log Pn equals to n log 10 minus n log n. And this gives us a nice clean function to work with. Step 3. We take the derivative. We use the calculus to find the maximum. Then we solve for n when the derivative is 0. And we get n equals to 10 over e. We use the first derivative test and know the product is biggest when n equals to 10 over e, or roughly 3.68 parts. Why is this important? Here's the cool part. Splitting 10 into 3.68 equal parts isn't practical, but it tells something amazing. If each part is close to e, the product is maximized. In the case of 10, for n equals to 4, each part is 2.5, and the product is the largest among all splits, because 2.5 is the most close to the e. The power of e. This is the cute e. Why does e show up there? It is not magic, it's math. E is the most efficient number for balancing size and quantity. It's the same reason e is used in compound interest and natural growth models. Nature just loves e. Now you can too. The last part, we are going to show some pictures about math meets art. Look at this one. This one is so beautiful. It is actually created using the transcendental numbers e and pi. The spiral side. Transcendental numbers like e define the curve's perfect expansion rate, creating a pattern that never overlaps, but remains in perfect harmony. The color gradient side. The other side features a vibrant gradient creating using the digits of pi. Each color corresponds to a digit 0 to 9, forming a unique sequence of shades. Together, these two representations, the structured barrier of E and the chaotic beauty of pi, show us how transcendental numbers bridge logic and creativity. From galaxies to abstract art, these numbers are everywhere, quietly shaping the world around us. Maths, after all, is the ultimate artist. These are the sample references I used. And thank you for listening. Bye bye.